Hi, welcome back. In today's video, we're going to go over a very quick exercise. Essentially, we've been discussing in the lecture style videos, right? These concepts now of pre-computed heuristics being these perfect distance oracles, right? Things like CPDs, well, they can tell us the exact distance to go. That sounds great, right? Now, however, we're also stepping into the idea that there are now dynamics in our environments, right? Obstacles can move, obstacles can change, things in your world, right, may change costs. The world is a much harder place, but of course this is really very often an actual situation in real problems, so we're stepping towards that aspect of realism. Now, in dynamic problems, okay, let's have a think. So let's consider the fact that we have already run a pre-computed heuristic. In the lecture, I'm telling you that in dynamic domains, well, it's really worthwhile usually to pre-compute an entire heuristic, right? The problems are going to be so hard, things are going to change, that we want to spend the time to create a good heuristic. Now, these heuristics are good in dynamic environments where the costs, right, cannot drop below some floor, okay? So in order to maintain an admissible and a useful heuristic, well, we need to compute our heuristic, our pre-computed distances, based on the lowest action cost floor, right? The lowest the cost could possibly be. Now, so how this relates to the conversation today, well, we're talking about the situation, right? Well, okay, imagine I've just pre-computed a heuristic. I assumed it was a base case, whatever, I've just done it. But now we talk about the idea that fixed obstacles in the environment that existed at the time of your pre-computation, what happens if they are dynamic? What happens if they disappear? So in a video game, say you compute your heuristics, and then all of a sudden someone knocks down a tree, they knock down a wall, or perhaps in this situation I'm going to be drawing, a door that was previously closed now opens, okay? What does this mean for our algorithm? What does this mean for our heuristics? Is search still going to be complete? Is it still going to be optimal? So let's dive in and consider the situation. So the way I like to think about this is I'm going to talk about two separate cases, right? So we have case one on the left here. This is a situation where in both situations we're starting at a start location outside, and then we have these two different cases, two different versions of a room. In case one, the goal is previously reachable, right? So there was some existing path that would be able to get us to the goal in the world that we've computed, we've done our pre-computation, okay? In case two, I'm going to then have a check. What happens if it was previously unreachable? There was no previous way that I could possibly actually get to arrive at the goal, and therefore, right, you would have computed some infinite heuristics, right, or you would not be. Okay. Okay. So I like to talk about this. So I like to approach this problem using two cases, right, to showcase the different ways and behaviors of our algorithms. So there's two situations. The first one being in the case that the goal was previously reachable, okay? So there exists a path that was previously able to arrive at the goal in our search space when we did our pre-computed heuristic, okay? And then things are going to be a little different, right? When things like this door, this shortcut starts to open up, right? We had assumed that we had done our pre-computation at a ceiling floor, but no, we find out that that was not the case. There will be a shortcut, okay? Then I also like to talk about the idea then that the goal in case two was unreachable. There existed no possible path, no way of reaching this node at the time of our pre-computation. So let's have a look then at each of these cases individually. In case one, the goal was previously reachable. Okay, so let's consider what search is going to be doing. If we have a look, okay, so this door here now, this door is open, a shortcut exists. We will be doing our regular A star, everything's kind of happy, right? Because the goal was previously reachable, well, we have a series of heuristics that are essentially vaguely pointing us in the direction, right, where we go around, we go through this corridor, this entryway up above, and then we beeline to the goal, okay? So this is still where search is pushing us, right? That's the the heuristic value is like this perfect distance heuristic, is going to point us the correct way. There is a bit of this, right, this slight fill-in behavior because we're still expanding nodes by g plus h, okay? Where in this case we're considering just doing a regular A star as opposed to CPD search. CPD search would have no fill-in, right? It directly follows the exact recommendation. But we're talking about using things like A star with the pre-computed heuristic as our standard heuristic just for evaluating the promise of each node. So we would have some form of fill-in behavior, but we'll be essentially going the long way. Now, at some point in time, right, as we continue doing this search, well, it may be beelining this way, but there will be some neighbor, right, that will be attempting to generate its valid neighbors, okay? So in terms of your code, right, you will have this expand function. It queries the map will return to you the grid map. Oh, okay, these locations were accessible. Now, one of those will be now this new location X, which was previously a closed doorway. The grid map, even though your heuristic was not aware of its existence, your grid map is going to return this as a valid successor, okay? But let's consider how it enters into the open list, right? How it's ranked in our search. So the heuristic value for this node, right? The heuristic we're storing is from every location, what is its distance to the goal, yeah? So we have this all pairs distance table, this CPD. So we have this all pairs distance table. Well, it's telling us from any location, any node n in the entire graph, what is the distance to the respective goal, okay? So from the doorway, it was previously blocked, right? So the heuristic value, the distance, the shortest cost path from this node x to the goal is infinite, right? It is obviously invalid. There was no valid path to reach this point. We have to give it a value, or give it max int or whatever else, right? So when we essentially are creating like an open list and we go to add this into the open list, we'll consider the idea that it will be ranked at the very end of the open list no matter what, right? All other nodes, we're assuming, right, maybe there's more doorways and maybe there's a few nodes with infinite values. We'll talk about that in a sec, and that relates to case 2 a little bit more. But every other node here along the way, as we kind of take the correct path, these have smaller f costs, right? Their cost so far is added to a finite heuristic, one that already knows that it can reach the goal. What this means is that the final path we're returning, even though we generate the doorway, we generate the shortcut, it exists in our frontier, we never take it, okay? We will always find and return the other version of the path that already existed. Now, so what does this mean for completeness and optimality? Well, hopefully you can see that if a solution already existed, it will still exist, right? We're talking about the idea of fixed obstacles disappearing. So there are new pathways, but the existing pathways still remain. In this case, the search is still going to be complete for sure. Now, obviously, the key difference here is that it is no longer optimal, right? The optimal version of the path, which takes a shortcut, yeah? This version of the path exists in this, well, the part of it exists in the search space, but we never ever expand it. We never look beyond it. We get to the goal, we expand the goal, of course, A star says we're done. So because this is absolutely not optimal. Okay, so that is extremely problematic. Obviously our pre-computed heuristics then have kind of not helped us in this situation at all. Okay then, so let's consider case 2. In case 2, the goal was previously unreachable, okay? Now, let's consider what that means for our pre-computed heuristic values. In the outside region, in the region, the connected component, you could call it, that is reachable from the start location, so all of this, including this upper room here, well, every one of these locations, they are recording the distance from that node to G2. Well, G2 was not accessible, it was not reachable, and that means that every node in this entire space is infinite. Its heuristic value is infinite, right? So what that means is the entire area here is going to be misled. It is providing no information. And worse, it's actually, because it's an infinite value, we'll see it's detracting from our ability to do search, right? Instead of just being able to rely on G costs, if we have a max int in these situations, well then it's erasing essentially also the information we'd actually even gather from G. To complete the picture then, what happens with heuristic values inside this box? Inside here, they are happy, right? They are finite, and they will be pointing correctly towards the goal. Because from inside this little room, there is a valid path directly to the goal. Okay, so that's interesting to note. However, so let's look at the behavior of search then. So I've just discussed that in this entire connected component region, right, anything that was previously reachable from the start location, these will have an infinite heuristic, right? What does that mean for search? What does that mean for our open list? That means every node is ranked with, yes, still the cost so far to reach that node, but then also with adding an infinite value heuristic. So usually this is probably, in a vanilla sense, right, this is going to be max int. What that means then is that obviously it was invalid, but it actually means that on top of everything else, we're losing the value. We're not even retrieving the search behavior of uniform cost search, because your G values are completely dwarfed by the heuristic, as well as the fact that if it's a max int in your implementation, all information is completely lost, right? It just remains, so max int plus G is just either, well, max int, or hopefully you deal with runoff there. So what that means for our search face is just that all of these nodes, the actual path that we're returning, I guess I'll start with the idea that, again, similarly, right? At some point in time, we will reach this node, right? I'll talk about the path to get here, but we will reach this node and we will again generate our new location X, the doorway that is now open. The doorway, as well, similarly to before, also has a heuristic value of infinity. Okay, so let's talk about then the behavior of search up until this point. If every node is ranked the exact same, right? Every node here is ranked always infinite, nothing looks good, nothing looks promising. Well, you will be doing this perpetual search in a similar way, but it's not based on G anymore, right? It's not these nice lines. You could be finding, sure, technically it could just still be you might just be finding like an optimal path, right? Here I was drawing it with curves, so maybe I should do that, right? It's possible to find the maximal path, but what's likely going to happen is that if everything is ranked the same, well, you're going to get some really silly behavior, right? It's completely up to however your tie breaking's working, or how your priority queue is implemented. You could be taking any version of this path. They all look the same, right? In terms of A star, it thinks they're all ranked the same, and so it doesn't matter which one you choose. You could choose some really dumb things. All of this is to say that once we actually get inside the door, well, we will beeline it to the goal, right? Okay. In this situation, this was just a very simple case where it was completely reachable, so that's fine. But hopefully what we're seeing is that, obviously, similarly to before, this is definitely not optimal. Okay, so we can talk about it in two different ways. Any of the path in this outer region, you could take a long detour, right? This is no longer optimal because we haven't ranked nodes in the correct way. A star is expanding randomly. Now, on top of that, this situation currently is easy in here, but this situation is also not guaranteed to be happy in a more complicated situation. So imagine there were more walls, there's maybe this case 1 situation also happening in here, or there is imagine there's another doorway over here, and it finds it first, but this one has like a whole maze it has to go through. So there's all of these situations. Essentially, again, it's just going to mean that we lose optimality no matter what. Even though there is this one case where you do find the optimal solution, the algorithm is no longer guaranteed to return that in any way. Hopefully you can see though, is regardless of the fact that you will completely fill in however much of this region is necessary before you randomly stumble on this node here, well, it will generate X, okay? So in the worst case, it's up to, it's up to tie breaking. But at some point in time, in the worst case, even if X is at the very, very end of the list, you will finally expand X. You will generate the valid child inside the reachable region. And that means that search is still complete, which might be surprising. But yes, you will still be able to find a solution if one exists. It's just that because of the obstacles disappearing, well, our heuristics, right, are completely caught astray. They're not providing us with useful information. Instead, they're completely wrong. So there's some implementation hacks and like asterisks in a lot of this explanation, but really the takeaway in this exercise is just that your pre-computed heuristics they really, really, really need to be based on a simplified version of the world where essentially you have correctly identified the lowest bound on your cost, right? The lowest the lowest cost floor that it can possibly be. In that world, things will be happy. We can really use these pre-computed heuristics to search favorably in a dynamic domain. In the case that obstacles actually disappear, right? So the cost floor essentially is dramatically lowered in these situations, or just is lowered. Well, then we maintain completeness, but our optimality vanishes quickly. Okay, so there is another side to this story though, right? I'm telling you, hey, in an ideal situation, I will pre-compute my heuristic with the correct cost floor, which means my heuristics will remain admissible. I'll still be able to find optimal solutions quickly. I've also said on the other side that when obstacles dynamically disappear, well, then our algorithms really enter into these very silly behaviors and they don't seem to be behaving properly. Okay, well, there's the middle ground. So in the rest of the regular lecture series, I'll continue onwards, right, with the ideas of how we better handle dynamic obstacles. But there's this other aspect of pathfinding for things like video games, maybe UAV navigation. But I think video games is the primary example here. In destructible worlds, say something like trying to pathfind in Minecraft, if you wrote an agent, maybe something like Battlefield, right? Dota, in these games, right, where you have these destructible environments, right, the player can absolutely just decide to remove a forest, remove a wall, to change the space in the environment. In a future video, I hope to also address maybe some of those challenges, right, because I think there are some small clever ways that we can go about then maintaining a functioning pathfinding system, even in these worlds, as obviously they do. So there's obviously ways, right, where we can hopefully identify things like connected regions, and then when you identify this merge, this changing of a shortcut, well, perhaps you now need to merge, dynamically update, and perhaps recompute heuristics for part of the world. So I think there are some nice tricks for this, and I just wanted to point that out, right, as like at times this is not something that you can avoid. And we will sometimes have ways to deal with this, dynamically recompute things, try to focus our attentions on just the things that need to be recomputed. And so there are some tactics for that. I just wanted to note that. But then moving onwards, hi, so thanks for watching. I highly recommend that you go have a look at the compressed path databases video, which really deals with this idea of an all pairs perfect distance heuristic, and then also continue on to this video where we have initialized these discussions on how we're going to be searching in dynamic environments, and we can start to tackle these problems. Thanks, and see you there.